Okay, so for this chapter, as I said, we have two things you need to know. One is this one here. We talk about this, right? We talk about the binding energy starting with this one here, that you have more of the proton in the center. You're going to increase the size of the nucleus, and this R here is the way that you can estimate the radius of the nucleus by looking at what is the atomic mass is. The A over here represent the atomic mass, and you use that number. You take the cube of that, and then you get the estimation of that. The R0 is a constant between 1 to 1.4, but normally we just use 1.2 times 10 to the negative 15, and you can do an estimation of that value. And then we use this graph to show you what is the binding energy of an atom. If the size of the atom start to change, and some place you're going to have the most stable one. The competition over here is the competition between the electric force and also the strong force. Okay, you have to know what the strong force is. The strong force is coming from the neutron. This is the thing that we believe the neutron contribute to the strong force. Strong force only work in a very small radius. So once the atom become larger and larger, strong force is not going to give you a lot of help. It will start to break the nucleus, and it will break down to smaller pieces. And the most stable element is the iron, 56, and that is the blue line that you see on this graph. We have two kind of a reaction, fusion and fission. So fusion is that you combine smaller things into larger things. Fission is that you break down things into smaller things. What kind of a reaction that we use for the nuclear power? Is it a fusion or fission? It will be the fission. So the fission that you start with the uranium, you're starting with the high, you're starting from this one here, then you break down into smaller pieces, and then and that's what we call the fission. Okay, fusion will be more like a hydrogen bomb that you combine two hydrogen, you can create a helium, and it will create a big energy as well. So these two all will create a high energy, meaning the reaction will create a mass defect. When you have a mass defect, which is the change of the mass, so the change of the mass will give you the mass to be smaller, right? Or larger or smaller. You're going to have the smaller, which means if you're starting with certain things and you calculate the mass of the total object and you combine it together, you make the subtraction and you find out what's the change of the mass. Now this part, as I said, you're going to have one question at least to ask you about the binding energy. So how do we find the binding energy? You're starting by looking at the change of the mass over here. And this equation over here tells you several different symbols. You have to know what those symbols represent. The N over here represents the number of the proton, the big N. The Z represent, oh no, the N represent the number of neutron, sorry. This big N represent number of neutron. Z represent the number of proton. The M of N represent the mass of the neutron. This one here, 1H represent the mass of hydrogen 1. These mass you can find it from the appendix of your textbook. Okay. The last one here represent the mass of the atom. And it depends on what kind of atom you're looking at. So the periodic table, you're going to need a periodic table. You're going to need a table to show you the mass for each one of the elements. So make sure that you have those things available. So when you are doing the exam, you know where to find those. Once you figure out the number of,
I have a question, Professor. For the chart that you said that will have like the mass of like the hydrogen, the neutron, how the appendix. Is it okay during the exam to have that part of the textbook open, or would you prefer to like copy and paste it on like a document and print it out?
it's open book exam anyway.
Oh, okay. That's what, I mean, because since it's like recorded, I just want to make sure it's okay or not.
Yeah, it's open book exam. You just
Okay.
Yeah.
Professor, if we're using an ebook, is that going to interfere with the proctor exam?
No, I think you could. Oh, that's a good question. I will make it not to interfere your exam. I will allow you to, open the link of the ebook.
Okay, thank you.
Okay. Any other question about this part? So if you have an ebook, make sure that you know how to find those table or those appendix. Okay. Now when you do this calculation, don't ignore any of the digits. These changes are very, very small, so you want to carry all these digits. Don't ignore any of the digit. Don't just I'm going to take like 3 digits at the decimal point. No, you carry all of them, because any of the subtraction, any of the change is going to create a big energy. So you don't ignore any of the digits. Carry all of them in the calculation. Okay, so we kind of did one example about this calculation, right? So any question about this, like this problem that we did before? So, so if you do the homework, again, the homework is due on Monday before the exam. After Monday, I will close the homework, then we will start to calculate your score for the homework. So the homework will be closed on Monday. No more homework for chapter 28. I'm not going to give you the homework for the chapter 28. So 27 will be your last homework. So when you do this one here, make sure that you look at this periodic table. You know how to find those information. How to find information about the proton. How to find the information about what the symbol that will represent. Okay. All right. I guess everybody know how to do this. So we also talk about this one here, right? So anybody try this one? Anybody has a question about this one here? Anybody didn't know how to solve this?
Can you go over that one, please?
Go over this one here, example
yes.
2?
Yes.
Okay, let's do this one here together. Let me change to my pad. Okay. So I have to change my pad. So let me see. Let me share from my pad so I can write. Let's look at this one here first. So two things you have to know when you solve this kind of problem. One is that you have to know how to, you guys can hear me, right? Just want to make sure.
Yes, but I think you need to share your screen or.
Oh, okay. I forgot this all the time. Let me share the screen first. Yes. Oh, set this one up. Okay, now let's try to share this one. Okay, is it good? Everybody can see it? Right?
Yes.
Oh, okay. I haven't changed to my notes here. Okay, so for the reaction is very similar to the previous one. For the reaction, the first thing you need to know is how to balance an equation, the reaction. You need to find what is the element in there, and are there like a multiple number of the particle will be emitted from this equation or not. So the way to figure it out is just simply look at the two numbers by this element. The element is the symbol they will put at here, like this one here is this element. Now the X is the unknown element we try to find out. This is another element, this is another element. I don't know the name of this element, but just treat it as a symbol. Then you look at the periodic table. So let's go back to the periodic table. So here is the periodic table. And the number on the periodic table represent the photon. So it's the number that we put on the left and lower bottom. So what is AM here? AM is this one here, which is 95. We'll put 95 here. The SR is, which one? Anybody find that's? Ooh. Anybody see?
It's in row 2 or
Row,
column 2. Sorry, column 2, 38.
Oh, yeah, 38. Okay, 38. Great. And the LA,
57.
what? 87?
57.
57. Oh, okay, 57. Okay, it's this one here. So now we got all these numbers represent the number of the photon. Then another thing you need to know is about different particles. If you have alpha particle, this is an alpha particle, is a helium, the helium 2 plus, which is ionized the helium. It has 2 proton, it has a 4 at this corner. It has a 2 photon with 2 neutron. So this is an alpha particle. If you have the beta particle, which is the electron, right? So beta particle, electron, then when you write the electron, this is the electron, you put -1 over here, and there's no proton, there's no neutron. It's just electron, so it's 0 on the top. This is how you represent the beta particle. For the neutron, you only have the neutron, so the neutron will be no proton at the bottom, right? But you have 1 at here. That's how we represent the neutron. Now these two numbers help you to balance this equation. And if you look at here, we just make the bottom number on the left equal to the bottom number on the right. That's how you balance this equation. So to find the value for X, let's say I have a 1 number here, I have another number up here. This is my A number, this is my B number. I try to find what is the A, what is the B. And I know this neutron over here is simply equal to the 4 and 0 and 1. So this is this neutron over here. And I look at the A number, I sum all the number on the top, 242 plus A equal to 90 plus 149 plus 4 times 1. At the bottom, I have 95 plus B equal to 38 plus 57 and plus 0. Okay, so now you can solve those two equations to find out what is the A and what is the B, and see what is the B. 95, 95, this is a 0. What? 80, that's 0. Okay, that's B. So what about A? So A is 242 minus 90. 242 minus 90 minus 149 minus 4. That is 1. Okay, so what is this one here? What does the X represent? That means my X has a 0 here and 1 in here. What is X? Isn't that just the neutron? Right? That is just simply just a neutron. So this is actually the neutron, 0 and 1. Okay, so this one here is the neutron, and then I'm going to replace this one by neutron and 0 and 1. This is a typical like a nuclear reaction. The nuclear reaction is that you start with a neutron. You use the neutron to bombard a large element, and you will create what we call the chain reaction. Why this is a chain reaction? Because you start with 1 neutron, but after the reaction, it creates 4 neutrons. Then each one of the neutrons has a possibility it's going to bombard to the next one. When you bombard to the next one, you're going to create 4 times 4 of the neutrons. So this reaction will happen very fast because you create this kind of chain reaction. It just keep on going, and energy will create in a very fast way because of this chain reaction. Okay, now the next thing we do is to find out what is the mass on the left-hand side and what's the mass on the right-hand side. Are there any different of the mass? So let's see what is the reactant. So you sum all these mass. So the one that we have is 242 plus 0.595,490. Okay, carry all of them in your calculation. What is the neutron? Well, it doesn't give you at here, but we actually told you in the previous example, this is the mass of the neutron over here. 1.008665. 8665. See? Yeah, 0.08665. The U represents the AMU, right? So this is the only one at the beginning. That's the total mass that you have. Now, this product mass is equal to everything on the right-hand side. So you have 89,907,387. If it doesn't give you this, then you have to look at the table. You have to look at the appendix, try to find all these mass from the table. The LA is 148 plus 0.937 at 4733 U. And the neutron, you have 4, so you have to use 4 multiplied with 1.008665 U. Okay. All right. So what do you do next? Well, I think the rest of things you just simply sum them together, you subtract them, and you got the final result. See if I have those numbers. If I don't, then I think we can do this calculation by itself. Well, I couldn't find it. Any question about this part? Let's see. I think I have it somewhere. Okay, I got it. All right, so I find out the change of the mass is equal to 0.1910823. Okay, and U. So that's the change of mass. If you sum the top one together and you sum the bottom together, you find the difference of these two, and you're going to find this. Okay, and then what you have to do is that if they asking for the energy and they wanted to find the energy in the mega electric volt, meaning you cannot simply answer the U. U is simply just the mass. How do you find out the energy? Well, the energy is equal to the change of mass times the c squared. So if you use the change of the mass times the c squared, you got the energy. But if you simply multiply these two together, you got the joule instead of the electric volt. So you have to get an electric volt. One quick way of getting this result is that you can change the mass in terms of the U as in terms of the megavolt per c squared. We give you this equation before, which is this one here. This is a conversion factor that you use to convert the mass into a mega electric volt divided by c squared. So 931.5. 931.5 mega electric volt divided by c squared is equal to 1 U. So you change this one in terms of the mega electric volt divided by c squared, and once you multiply with the c squared, whatever the value that you got is going to be whatever the energy is going to be. So this will be equal to 178 mega electric volt divided by c squared, and you use that multiply with this one here, then you got 178 mega electric volt. Okay, any question about this problem here?
No.
Okay, good. So work on some of the homework, and then you hopefully that you understand how to do this. As I said, this is definitely going to be one of the questions in your final exam for this part. Okay, the second part is about the half-life. We talk about the, I told you the story about the Iceman already, right? And if you look at the book, actually textbook also uses this example. He is so famous, so it's a very good example to tell you about the carbon dating and give you an idea of what a half-life looks like. So one of the things that we understand about half-life is that you learn this one probably from the chemistry as well. The half-life simply meaning is the time interval for some like a radioactive sample would reduce its nuclei by half. So if we define a half-life, we use a symbol to represent that, and the T, capital T, is like a period, is also represent how long does it take for this amount to reduce by half. Okay, so what is the unit of this? This unit is time. So unit is time. The time could be second, could be days, could be hour, could be year. It depends on what the time they give you. So be careful about reading what is the unit of this. Some of the things will have a half-life within seconds, even milliseconds. Some of the things will have years, even thousands of years. Like carbon has a 5,370 years. I think yeah, that exact number is that number. So it depends on which kind of element you're looking at. Now the half-life has this idea. So this picture that shows you is the bottom represent the time. The vertical one represent the amount of some kind of material. So this is the amount. Normally, when we represent the amount, we will use the n to represent the amount. So that would be the n. And the bottom one is actually the time. And they put a capital T and 2T, 3T simply represent at that mark is 1 half-life, 2 half-life, 3 half-life, and 4 half-life, etc., etc. Now, sometimes they don't give you the equation or give you the number directly. Sometimes they give you a graph. So if you got this graph, you have to understand when time goes to 0 is where you start with. So this one, n0, a lot of time in the equation, which is right n0. N0 is meaning at time equal to 0, what is the number of the nuclei that you have, that you start with, or the amount of the radioactive material that you have, maybe in grain, maybe in mole, maybe in number of the particle, number of the atom of the material. So this N0 represents the original amount, the starting point that you have. After one period, you're going to reduce half. So how do you find a half? Well, you look at this bar here, represent the total length, and you just simply cut it in half. That will be the half. So this is 1/2. This is A0 divided by 2. And that is where the one period should be. Now, this next half-life, let's say T is 10 days. Then at the 20 days, you're going to reduce another half amount. It's not like another half. It's, well, the another half meaning you multiply A0 divided by 2 by another divided by 2. So this is going to be the second period. Based on this idea, then we can come up with a way. If you simply give me how many of the half-life, let's say T is the time, okay? And if I can represent the time with some number times my half-life, well, by the way, in the book, they use different symbol. They use tau 1/2. This is the same as my T over here. Okay, this is the half-life symbol that they use in the book. So T is half-life. This T, this small t represent the time period, the time period starting from 0, okay? And this n here represent the number, how many of the half-life, the equivalent to T, okay? Okay, so for example, let's say I have a something, the half-life is 10 days. And I wanted to know if I have a half-life is 10 days, but then I look at the material after 50 days and how many of the N there should be. That's very simple, right? So you start with the 50 is the time period that you're looking at, and you look at how many of the time period, how many of the half-life you've been going through. Where the big T is simply equal to 10, that should be 5 times 10, meaning your N is equal to 5. Now, what if I don't wanted to, I not only just wanted to find this, what if I wanted to know what other things remained after 5 of the half-life? The substance remain will be based on this equation. So let me write down this one here. The things that you left is the N is going to be the amount of the nuclei that you have after a certain period of time. And it's going to have a ratio of this, and based on how many of the half-life that you pass through. Each one of the half-life is going to give you 1/2. If you have 2, it's going to be 1/2 square, 3, 1/2 cube, etc., etc. So 1/2 to the power of the N is the way you can figure out how much of the material that you have left. Another way you can write this is that if you wanted to know how much amount that you have left, you simply use the N0 divided by 2 to the power of N. So for this example that we show you, if you want to find how many of the things still left, then you can find out the N is equal to some M0, which I didn't give you the M0. Let's say let me give you like the mass of the material. That would be 1 kilogram. Then you're going to use 1 kilogram divided by 2 to the power of 5. Okay, so that will be how you can calculate what is the things remains after this amount of the period, and how do you solve this. Okay, any question about this one here? So that will be 0.03125. Okay, so after 50 days, you only have this much of the radioactive material left. That's what it makes. All right, so this kind of looked like a very simple. Now, if we change this one to another way to describe it, so we kind of describe what a half-life is. The book used the tau/2, and I use the T, the capital T, represent the half-life. Another thing that you will see is that we can also describe the so-called the decay rate. Okay, so what is the decay rate? The decay rate meaning how fast would this amount to be reduced, to decrease. if you look at a graph right now, if this is a radioactive material, would they decrease the amount at the same kind of rate? Okay, let me write down the decay rate first. The decay rate is the symbol A I use at here. The decay rate is the number of the amount will be decreasing over a time period. So this change of N represent the change of the amount, the change of the material, the change of the nuclei that you have in this material over a time. And this is the time. This is the change of the time. This is not like half-life, but this is related to a half-life. This is the amount, okay? So what is this equal to? Well, this is equal to this. This is another equation you have to pay attention to. So this decay rate is defined by this. The decay rate is not a constant. The decay rate depends on what is the amount at that moment. Okay, so the so N is the current amount. It's not a starting amount. The starting amount that we will use N0. The N could be depends on what time you're looking at. If time is one half-life, that will be half of the original. If it's a 2, then will be a quarter of that. So the N is not a constant. Don't think about the N is constant. This lambda over here is another terminology that we have to define. This is called the decay constant. This decay constant is a constant. Okay, this one doesn't change. N will change, but lambda will never change. But how do we know lambda? What is lambda anyway? How do we calculate lambda? Now, this one here is another equation that can help you to find what is the lambda. Well, lambda is equal to 0.693 over half-life. Or you can also say, if you know the half-life, you use 0.693 divided by the decay constant, and that will be equal as well. So these two are the same thing. As somebody told you, the lambda times T is equal to 0.693. Okay, this is called the decay constant. The decay constant. They are all the same unit. The unit, there are different units. The T, the half-life is a year. The lambda is going to be 1 over time. So that the lambda is 1 over time. The unit of the lambda is 1 over time. The T has the unit of time. Okay. So what does the lambda represent? If you have a lambda is larger, what does that tell you the rate of the change? If you have a lambda is larger, meaning that if you look at this decay rate, you can see lambda is larger, meaning you change the number of the things left will be larger, meaning you change larger, meaning you're going to decay faster. So A larger lambda meaning the decay is faster. Why do we put a negative sign? This negative sign over here represents as decreasing. That's why you put a negative sign over here. Remember, this is negative over here, okay? Negative, meaning this is a decreasing because the radioactive material will keep on reduce the amount, so that's negative sign over here. So let's look at how we can use these. Now, there is another equation, which is this function over here. So several different equations. These are only the equation that you need. And then after we introduce all these equations, let's look at some example over here. Okay, the next equation is this. For those of you in the honor section, the handout that I posted is how do you derive this equation based on the calculus. So n is equal to n0 multiplied with this exponential function minus lambda times t. So n, this n here is amount left. In the book, they use different symbol. I'm sorry about that. They use R. Okay, if you see R and R0, is the same as the N and N0 that I'm using. So M0 is going to be the original amount. Again, the amount could be the mass, the amount could be number or more, the amount could be the number of the particles. It all represent the same thing. Okay, do you guys have a calculator? Be able to calculate this one here? Okay, make sure that you know how to do this one in your calculator. If you have this problem, you have to know how to enter this to get the result of this. One interesting thing you look at this equation is if you starting from 0 and time go to the infinity, what happened to this result? If time go to the infinity, meaning this go to infinity, you're going to have this one go to a very, very small number. It's going to make this n to be 0, meaning after a long time, the radioactive material will eventually go to 0. That's what that means. Okay. All right. Question about these three equations. Okay, I will introduce a bunch of equations. Let me recap some of the things we told you. One equation here. If you given with the amount of time, and you can calculate how many period it passed through, right? And then you can calculate the amount left using this equation. But this one only valid when you do like a n is integer. If n is not integer, like not 50 days, it's 49 days, then you have to use different equation. That different equation is actually this equation over here. This one, you simply put what is the t in here, the 49 days, you put 49 here. How do you get lambda? Well, you get lambda from here. Sorry, my screen is a little bit messy, but these are the main equation that you need to know how to do the calculation. Okay. Any question about this part? And the decay rate is defined as the change of n over change of t, and that will be also equal to negative lambda times n. Do you think the decay rate is going to be the same? Is the a constant?
No.
A is not a constant. Do you think A will be larger and larger or smaller or smaller?
Smaller.
A is going to be smaller. Lambda is a constant. And lambda has the unit 1 over time. Lambda can be calculated by the t, so 0.693 over the t. In the book, they use nature log of 2. That is the how you get a 0.963 coming from. Okay. All right. Question about this part. Okay, let's do some of the example over here. Okay, now here we have a graph. They didn't tell you the half-life. They didn't tell you what is the lambda. They only give you the graph, but they show you how much amount of the material will become after a certain time period. And we want to find out, can you estimate what is the half-life of this material? Okay, so you look at here, this one here represents the amount, and we start with the amount, which is 100%, right? So the way to find a half-life is that where it's going to be when you reduce to half amount. The half amount is the 50%, so we look at the 50% somewhere around here. So this will be 50%, right? So when it goes to the 50%, then I can go down to the time, and I can tell you what is the half-life. Now, if you just look at this one here, maybe that's not good enough. It's not easy to identify because the scale is not like very precise. You can do another estimation to get an average such that you get a better estimation of this. So what is the next period that you're going to have? Well, the next period is going to be 25%, right? So the 25% is going to be, so this is a 20, where is the 25? This is a 40. So 2, 3, 4, 5, there's a 5 of them. So that's 4. This one is 24. Oops. Okay. The smaller scale just right above the 20 is actually 24. So if you just go up a little bit, then you can get the 25. Right. So this is a sorry, buddy. Okay, it doesn't work. Okay. Any question about this part? My pencil just died. So what do you think the half-life this will looks like? How do you estimate what do you think the half-life looks like from this graph? Just look at a scale that you probably can estimate is about, I would say like a 7 point something. It's a little bit less than 8. So it's less than 8 minutes, but it's very close to 8 minutes, right? If you do another estimation, then you might get a better estimation. So this is going to be the second one. So this is 10, 12, 14, 16. That's probably like 17 minutes. So 17 minutes give you like a 2 half-life. So my half-life is about like 8.5 minutes. Okay, question about this part. Okay, if I give you this graph and say, can you tell me what is my decay constant, and how do you find a decay constant? What is decay constant anyway? What is the symbol that we use for decay constant?
The lambda?
Yeah, it's the lambda. The lambda is 0.693 over t. That is your decay constant. Okay, it's a positive number, so if you use 693 divided by the 8.5, and that will be 0.0815, and that will be 1 over a minute. That will be your decay constant. Okay. If I say, can you tell me what is the amount left? What is the amount left if I have this one go through, let's say, 20 minutes? How do you find that amount left after 20 minutes? Which equation that you're going to use?
You're going to use the n over n naught equals 1 half of to the power of n.
How do you find the n?
Oh, well, can we use the t for like time equals n 2 times a half-life?
So when you use the t equal to n times capital T, that has to be an integer. So it's not an integer.
Oh, okay. Hold on.
So you cannot use that. Okay. So be careful of this. If that is an integer, then yes, you can use that equation. But most of the time, it's not going to be an integer. If it's not an integer, then you have another 3 equation over here. Which one is the best candidate that you're going to use? What about the last one here, the exponential form? It's not like a common equation that you will see, but in this chapter, you're going to use this equation a lot. So make sure that you know how to use calculator to find out. So I wanted to say after, what did I say? Like 20 or 50? 20?
20.
Yeah. After 20 minutes, what is the n equal to? So use n after 20 minutes is equal to your original amount multiplied with the exponential minus lambda t. Lambda is 0.0815 and minute inverse multiplied with the time, and time is 20 minutes. And the minute will cancel out, and that is the equation that you're going to use to find out what is the result. Okay. Any question about this? Let me do some calculation. If you have a calculator, make sure that you know how to calculate.
For when you calculated the half-life, where did the 2 come from? Is that just because it's half of what you had?
Where is the 2 come from?
Yeah, the 2t.
Okay, it's from the graph. I know this point is going to be the t. This point, which is reduced another half, this is 25%.
Okay.
It's a 50%. So that has
Okay.
2t over here.
Okay, thank you.
So if you have a calculator, if you try to do this calculation, see if you got the same number that I have over here, 0.0815, and I got, is that right? Negative 0.0815. So it's N0 0.92. Doesn't look right to me. Did I do something wrong here? Okay.
When you know
Oh,
how
I
for
forgot.
the
Oh, I forgot to modify it was 20. Sorry. Yeah.
with the oh no, never mind, never mind.
Okay, let me write this slowly so you can follow me. So this, you have to modify 20 with the negative 0.0815. So I forgot to modify 20. That's why I got a very weird number. 5 times 20, you got 1.63 minus 1.63. And then you calculate what is the exponential to the negative 1.63. That is N0 times 0.196. What that means, you're going to have approximately like a 20% left. Okay, so you look at the graph. This is a 20 minutes, and that's approximately like a 20% left. Okay. Okay, question about this part. All right, let's look at another example over here. We have a sample of the material have this amount of a particle radioactive in today, and your grandma measured that has that much amount, and your grandma measured that 100 years ago, and how many radioactive material will this sample have after another 100 years? So from this information, how can you tell what is the half-life of this? What would be the equation that you're going to use to find out this? Well, you look at this one here that we know the N over M0 that is equal to 1 over 2 to the N. Even if you don't do this one, you look at this problem, you probably can figure out, well, you start, like your grandma measure like 80,000, and you measure that is 40,000. That's amount of half, right? You reduce about half amount. And how long does it take? 100 years. So you can kind of know the T is equal to, or the tau over 1 over 2 as half-life is 100 years. Because you reduce the amount by half. Now, after another 100 years, how much amount left? Now, you start with 440,000. That's your starting point. And if you make the N0 to be the starting point, you try to find what is N equal to, and you know the T is 100 years. And how many of the 100 years after? Just one. So you can find out what is the N equal to. N is equal to your N0, 40,000, over 2 to the N is equal to 1. So that is 20,000 particle left after 100 years. right? If you're looking at 200 years after, then you are looking at the n is equal to 2. So you are going to be starting from 40,000, and you have a 2 to the 2, that will be 10,000. That will be the amount left after 200 years. Okay, question about this part? The next one is very simple. I will let you try. Let's simply tell you the half-life. This is a T. And wanted you to know was 120 years afterwards. And just simplify the n, right? N is equal to 120 divided by 30. You got 4, and you can figure out what amount left. Any question about this part? Okay, let's look at another one here. I have a sample of this material, and it has a half-life of 6 hours. And the sample delay for 15 hours before it arrived to the lab, meaning I start with certain amount, and the half-life is 6 hours, but it reached to the lab after 15 hours. How much of the fraction left when it arrived? Okay, so how do you do this one here? Well, you can use the exponential function because this is not like a simple like an integer, right? Even if it's not integer, you can still use that equation. Just like I'm not sure that you you are able to calculate. You are able to use the calculator to enter that number. But if you wanted to use the exponential function, then the way we use the exponential function is you need to write down all the information that you have. 6 hour is what? Is which symbol that you were using it here? Is the lambda or the t or the small t or the n?
Isn't it the T?
Yeah, it's the big T here. Okay, so this big T represents the half-life. Now after this, we look at the 15 hours. What does the 15 hours represent in our equation? It's the small t Okay, the small t. Now we want to find the fraction of the TC left, is the material left. So the fraction is meaning that you have the amount over the original amount. I want to find this. I starting with certain amount after 15 hours. This is the amount after 15 hours. And N0 is my initial amount. I want to find what is this value equal to. Okay, now, again, you actually have two options. One option is you use this one here. But the n is not going to be an integer. Actually, you can still use this equation even though n is not integer. Just make sure that you know how to do a 2 to the power of some fraction number, not like an integer. So if you use this one here, n is equal to 15 hours divided by 6 hours, and that will be 2.5 hours. Another way you can do it is to use the exponential function. If you use the exponential function, that function is n equal to n0 e minus lambda t. That also tells you n over n0 is equal to e minus lambda t. So you can use this one to calculate that. If you use this one here, then you're going to have e minus, what is lambda? Well, you have to figure out what the lambda is, right? So what is lambda? 0.693 over this big T over here, which is 0.693 over 6 That is your lambda. Okay, so this will be 0.1155 per hour. Then you put this lambda over here, 0.1155, and multiply with the time, which is 15 hours. And that will be the fraction that you have left. Okay, if you multiply this, you're going to have a 0.177. It's going to be the same as this one here. Will be giving you the same amount. Okay, any question about this problem? Okay, let's do one more, just a little bit different one, and then we will move on to the lab. So let me write down one example here. So let's say we have a radioactive sample. Okay, and the sample initially it undergoes this kind of a decay rate. It's a 4.8 times 10 to the 4 decay per second. And 24 hours later, the decay rate changed. It changed to this number. Okay, and we want to find the half-life of this material. Okay, so how do we approach this problem? What does this give you? What is the number that they give you? What is the number they give you? And if you look at the equation that we told you before, what all this number give you? The decay rate is the number that they give you. It's like a change of the number over a change of time. So they're giving you the decay rate. Okay, and the decay rate, they give you that equation, A equal to minus lambda n. Let's write down this. Okay, so A is not a constant, right? We keep on emphasizing A is not constant, and A will decrease. As you can see from this number that they give you, starting from 4.8 and then drop to 1.2, so it will decrease. And the time period they give you is 24 hours. How do we find the half-life? Do we have a half-life here? No. So how do we find this? Well, if you just look at this one here, we know A is equal to minus lambda n. N is the amount left at that period. It doesn't have to be the original, but it's that period that you look at the amount. it probably start with some original, but it's not like exactly equal to 4.8 times 10 to the 4. It doesn't really actually give you the M, but it gives you the idea of what that is. So if we think about what would be the amount left, we can start with some number which is equal to, we have another equation, which is this equation. This equation is going to help us. This equation said that if you have something that you start with after a certain period of time, and I can calculate the amount left, right? So I can put this one into my decay rate. I can write my decay rate in another way. So I can simply say, well, my decay rate is change n over change of time is equal to minus lambda of n. And I'm going to replace the n with my exponential function. I got minus n lambda n0 e minus lambda t. Okay. Now, after this, I still don't know the half-life because over here, I don't know how much time is. I only know the time has been passed for 24 hours, but I don't know the N0, I don't know the lambda. So I have to, and how do you find the lambda? Again, the lambda is equal to 0.693 over T. I don't know the T. The T is the thing I try to find. But if I find lambda, I can find the T. So my goal here is, can I find the lambda? Then I can find this T. This one is the A. Wow, this is the one that they give you. They give you this A at a certain time. Let's say this is the A of T1. They give me another A. This A is T2. And I can write, say, AT1 is equal to 4.8 times 10 to the 4 decay per second. And that is equal to this one here. Okay, now same thing, I can write AT2, that is equal to 1.2 times 10 to the 4th decay per second. That equal to minus lambda n0 e minus lambda t2. The n0 is the starting point, which I don't know yet, but I can assume there is going to be some starting point, which is the n0. And if you look at these two, and I got a number for AT1, I got a number for AT2, and why don't we just take the ratio of these two? If I take a ratio of these two, I can take the ratio on the right-hand side as well, right? If I take the ratio, that is simply 4.8 times 10 to the 4 over 1.2 times 10 to the 4. And that will be equal to something on the right-hand side. What is the things at the right-hand side? Well, most of the things can be canceled out. I only have this one left. Okay, anyone know what this equal to on the right-hand side? Exponential something divided by exponential something else. If you have exponential function, if you have like a e of a divided by e of b, that is equal to exponential a minus b. If you have an e of a multiplied with e of b, that is e of a plus b. That's how we do the calculation for exponential function. So over here, you have divide, and that means your result is going to be e minus lambda t1 minus the bottom part, minus, and because there's a minus sign over here, it's going to be plus lambda t2. Okay, any question about this so far? Okay, so let me simplify this one. This will be e of lambda t2 minus t1. Okay, so on the left-hand side, if you take the ratio of these two, this gives you 4. What is the t2 minus t1? That's how much time does it take from the 4.8 to 1.2. So that is the t2 minus t1. So that is e lambda of 24. How do we solve this?
Don't you take the natural root on both
Yeah,
sides?
you take the nature log at both sides. You take the nature log at both sides, you're going to have the nature log of 4 equal to the nature log of exponential. The nature log of the exponential is the exponent of that, which is 24 lambda. That gives you the lambda is nature log of 4 over 24. And then you can find out this number over here. This will be 0.0578. And that is the lambda represent. And that is going to be per hour because we're starting with 24 hours. Okay, now this is not the final answer. The final answer is we need to find a t, which is the half-life. That is 0.693 over lambda, and then you take this number over there, you got 12 hours. Okay, question about this? I think this is the hardest part of this whole calculation. Are we all good?
Yes.
All right, if you see there's a chat, let me check the chat. Otherwise, we're going to prepare for the lab. No value is 100. What is that? Okay. All right, so we're going to have, let's have like 20 minutes break. Let's start the lab like 2:35. Sounds good?
Yes. Thank you.
All right, so let's come back at the 2:35 and then we start the lab.
Dr. Chow, you said that you send the honor section the n equals n not e to the how you derived it. Where did you send it on? Like on Canvas? Or?
It's on Canvas. It's under the modern physics exam folder.
Oh, okay. Okay, thank you.
So